Hello, math humans. We're going to do 8.1 today. We're going to be reviewing some of our basic integration rules. Really what we're going to do is we're going to go back and remember some rules that help us rewrite an integral so that we can actually do the integration. So the helpful hint, the first one that I'm going to recommend, and actually it's not my recommendations, it's your book, but the first one is expand the numerator. So if you had 1 plus e to the x and you squared it, then maybe you could split an integral up into 3 different integrals or integrate the 3 terms independently. The second one would be separate the numerator. So in this situation, I can split this up into 2 separate fractions, and then the integration is fairly straightforward. The third method is managing completing the square in the denominator. This resembles an arc-trig problem, but it's not quite there. So if I did completing the square and got to here, now it's just a simple arc-trig problem, and the integration is really straightforward. The next one would be dividing improper rational functions. And I would also add if the degree is higher in the numerator, like the one that I have here, okay? So even if the degree is the same, you can do long division and write as a quotient plus a remainder. You could do the same situation here, and then that often makes your rational function easier to integrate. The next method would be adding and subtracting so that the net effect is 0 terms in the numerator. This is the one that I tend to forget about. But let's say this was my thing that I'm going to integrate, and notice that I added a positive 2 and a negative 2. It then allows me to separate the function into 2 parts. I could factor this one. I could take out a 2, and then one of the x plus 1s is going to go away. I could do the same thing over here, and this one is simple u substitution. So it's another way of simplifying our problems that we're going to integrate. The next one that we might talk about are using trig identities, and primarily the Pythagorean identities. So I'm talking about cosine squared x plus sine squared x is equal to 1, and then 1 plus tangent squared x is equal to secant squared x, and 1 plus cotangent squared x is equal to cosecant squared x. And then potentially rewriting something like the tangent of x is the sine of x over the cosine of x. And I won't go back through all of our trig, but these Pythagorean identities tend to be really helpful. The last one that I have is multiplying and dividing by a Pythagorean conjugate. So let's say this was part of your integral that you were going to manage, okay? And then I multiply by the conjugate. So in the denominator, I have a difference of squares, okay? And then I can now have this situation. I can split it up into 2 fractions, and then I can do the integration. So the next thing that I want to do is just walk through some examples, not necessarily solving each of the examples, but just going through and showing things that you might want to consider as you try to set up the integration. On this one, u substitution doesn't work because there's no x in the numerator. This one is just a simple arc tangent problem, okay? So it is an arc tangent problem where your u is going to be equal x and your a is going to equal 3. And then the 4, of course, is just the constant that we move out front. So we would rewrite it like this, and then it's fairly easy to integrate. Okay. The next example is a variation of the same problem. And so what if I had the integral of 4x over x squared plus 9 dx? Well, now it's just simple u substitution, because if your u was x squared plus 9, your du is 2x dx. I could manage the numerator and then integrate by using simple u substitution. Example 3 is yet again another slight variation of these 2 problems. And let's say I had 4x squared over x squared plus 9. Now notice that the degree is the same, top and bottom. So what I would start with is long division. So if I divide it into 4x squared, if I divide x squared into 4x squared, I get 4, multiply through, and I get 4x squared plus 36. Change the signs, and I get a negative 36 is the remainder. So I can write this as a negative 36 over x squared plus 9, and then the quotient along with the remainder allows me to rewrite my integral. So it would be 4 minus 36 over x squared plus 9 dx, and then I would split those into two integrals and do my integration accordingly. Okay. All right, example number 4, if I remember right, it's not a variation, sad day, I didn't remember right. So this one I want to integrate from 0 to 1, and I have x plus 3 over the square root of 4 minus x squared dx, okay? So on this one, I could split this up, and I would do 0 to 1 of x over 4 minus x squared dx, and then I would do plus 3, 0 to 1, 1 over 4 minus x squared, whoops, forgot the absolute, or the square root dx. This one is going to be u substitution, where your u is your 4 minus x squared, and your du is a negative 2x dx. So that's simple to manage. This one is going to be an arc sine. So splitting the function up into two separate entities made the integration a little bit easier. Okay. Example number 5, we're just flying through our examples. If I have the integral of x squared over the square root of 16 minus x squared, okay, so on this one, I can, oops, sorry, I wrote that badly. I was going to say that doesn't work. It's x to the 6th. Okay, so in this one, I'm going to let my u equal x to the 3rd, because x to the 3rd squared is going to be x to the 6th. My a is going to equal 4. And then this is just going to be it's just going to be arc sine. Because when I do my du, I'm going to get 3x squared dx, which is your numerator, manage the 3, and then it's a simple problem to finish with arc sine. Okay, so example number 6. Alrighty, what if I have the integral of 1 over 1 plus e to the x dx? So I'm going to rewrite this one. This one is, again, that same type of problem that I forget to think about. And if I added an e to the x and subtracted an e to the x, net effect is 0. And then I divided by 1 plus e to the x dx. Well, now I can split my integral up into 2, and so I would rewrite it as the integral of 1 plus e to the x over 1 plus e to the x dx minus the integral of e to the x over 1 plus e to the x dx. This one simplifies to just be 1, so this is the integral of 1 dx minus the integral of e to the x over 1 plus e to the x dx, and this one is just u substitution. Okay, so being able to add a term, add and subtract, so that the net effect is 0 can really be effective. Okay, example number 7. So I'm going to have the integral of the cotangent of x times the natural log of the sine of x dx. So as I originally look at this problem, I might think that I can let my u equal the cotangent of x, but my du is a negative cosecant squared x dx. Well, that doesn't work. But what I'm going to do is the opposite approach, and I'm going to let u equal the natural log of the sine of x. My du is 1 over the sine of x times the derivative of the inside, cosine of x dx. Well, cosine divided by sine is cotangent, So then this just becomes the integral of u du. So that was actually pretty nice and straightforward. All right, I have one more example. So our last example, example number 8, I'm going to have the integral of tangent squared 2x dx. We really don't have an integration rule, at least at our level, for tangent squared. So I'm going to split this up using a trig identity, and I'm going to rewrite it as 1 plus secant squared 2x dx. Okay? Sorry, bad math. I'm going to write it as secant squared 2x minus 1. My bad. There we go. So now I have an integration rule for secant, so my u could be 2x. So then it's going to be pretty simple. But I needed to rewrite this particular function so that I actually had a rule, because I have an integration rule for secant squared. Okay? Alrighty, I think that gives us a great place to start Chapter 8. I will see you soon.